Okay. Yeah. Oh yeah. So yeah, I think last time we stopped where we're diving into like
Yeah.
updates.
So we're looking at, let me start here. We looked at this update function. We found out that what happens in a transaction is basically appending all the actions into a list, which would then be handled later on. So, but that the main magic happened in commit. And in this commit and send, we found out that at the end of the day, all the transactions actually just get all the transactions and actions that happen within the, yeah, all the actions that happen in the transaction just get written into a channel. It's in here. Yeah, here, right channel. But in the channel, so there's this function which listens on that go routine. Where is it? Yeah, it listens on that right channel go routine, and then we realize that okay, so here it's just a lot of logic to pull to get all the entries from the channel in batches, and then it performs the actual write operation inside of this function, write request. And we realized that in write requests, what happens was that, so first of all, it would write all of the requests, all of the entries into a value log. And I think when we checked this value log, we saw that it was just a file, which we were basically just writing, appending, like we encode everything and just append it at the end of the file. Yeah, that's mostly what all of this logic is for. Fancy ways of encoding everything and building the byte buffer and stuff. Yeah, but in the end, it just writes everything to the file. I think we took a look at the value log, and we saw that all, like for those test operations, all of the keys which we persisted, the keys and the values were all in here in the value log. Let's go back. Yeah. So we're writing to the value log. Then after writing to the value log, the next thing that happened is to write the entry into an LSM tree. And we had already seen this this. Sorry, give me a second. I think I should wear my headset. Computer is raving now. Okay. I can hear. Can you hear me? Can you hear me? Hello? I'm not sure if. Can you hear me? I'm not sure if I'm audible.
Sorry, can you hear me now?
Now I can hear you.
It's sorry, my headset has been acting off. I don't know, it's disconnected.
Okay.
Okay, so what I was saying was so one thing we didn't look into was there's this flushment task, right?
Yes.
Yeah,
Yes,
because
I'm
yeah,
actually almost there. That was in here. Uh, It happens inside this function, ensure room for rights.
yeah, it does
Yeah,
well. I
flush
mean,
chat.
this guy just it pushes the flush channel, but the flushment task was run.
Yes,
Um,
it's a good thing.
is a go routine that keeps listening to the flush channel task. So I think that was what we missed last time
Yes,
because we're
yes,
like,
yes. I was just trying to give like a rundown up to there. So let me just continue the rundown. I'm almost done anyway.
yeah,
So last time, so we saw how it was writing, it writes the responses to an LSM tree. And we already saw that the LSM tree is basically um, it's basically a data structure known as a skip list. We looked at what a skip list is for, which is a kind of linked list which much faster reads, or searching is much faster than in a linked list. And yeah, so pretty much this is it. So writing result is pretty much, the process is pretty much that of writing new entries is pretty much putting those entries within this skip list. But before we write to the wait, I think I just jumped backwards. Before we write to the ls entry, which is pretty much the skip list and all, we usually check if the size of the current list is, I don't know, at a particular threshold. So if it's at that particular threshold, then we would know whether to flush the current skip list, the current memory, the current LSM tree into disk. And that's where, when it's time to flush, we basically take out the skip list, which is here, and put it into this struct, and then write it into the channel. So it's inside this channel now that it now gets persisted. So
I think it's like
yeah,
flush mem something.
we have flush mem table, yes.
Yeah.
So it's in this flush mem table that we then persist that memory. Every time I see this empty, I want to say memory table, and I'm most likely correct. But then my brain is telling me to say skip list.
Well, I mean, it's a skip list behind the scene.
Yeah. So yeah, here we just look through all the results that are coming in through the channel, and then persist them to this in here, handle flush task. So here, there's a lot of things happening, and hopefully you understand this much more than I do. But I would just
I mean, it's pretty well commented.
wow. Thank you for that information.
It was nothing.
Okay.
Um, yeah, like I guess probably maybe playing around with it. I think it was this L0 table that kind of, because I was trying to. So I think the L0 table, they basically like squished. What's the word? Like they took all the items. I mean, like I think the summary is they took all the items in the skip list,
Yeah.
right, and iterated through everything
Yes.
and added everything to some sort of table builder, like the keys
Yeah.
and values. And then the table builder now does its thing by compacting all the values into a binary format. So yeah, okay, yeah. Also, I was going. I think this builder kind of got me lost because there were so many things they do checksums and
Yeah, there's a lot happening.
in the builder.
Yeah, but I think the builder is trying to build a block. I found that badgers and actually most databases like this, they write in they write to disk in blocks. So even when they are searching, when they are trying to find a result in the database, they search in blocks. So they find a block and then they maybe do a binary search within that block. So maybe that's what the builder is trying to create.
Yeah. And then yeah, so I think this was also when the whole protocol buffer logic comes in, where they include,
Yes, I saw it. So see a block one, block two, block three, block four.
and then they had the checksum at the end.
Yeah, with a bloom filter in there. This is pretty cool. I think this is a very interesting thing. So, I mean, I've not read the code in details, so I'm
Yeah, but we
guessing.
can go through quickly. I think so. Start. Let's. I don't know if you've gone through the old build L0 table, right?
Yeah,
I think I just tried to summarize this quickly, but yeah, I mean that's basically what it does.
yeah,
So
but in this builder, what I'm seeing looks interesting. So basically, we are building some binary blob.
yeah,
But if you notice here, they created a bloom filter with all the key. This,
the
yeah,
hash.
yes, with all the key hashes. So I think the idea is for each block, maybe the idea is that
You quickly run
when
through them.
you can run through all the blocks and just check each block if any of those blocks contains the keys you want. So you don't
Or
have to do a
might
binary
contain the
might.
keys you want.
Yes, might. and and then you can, if it might contain the key one, then you can binary search on it instead of binary searching on every single block, which is interesting. B.wg.wait. German is getting to me. B.wg.
Yeah, I think that's a weight group or something.
Yeah. Okay. Okay. So look over the block list. So the list of blocks. Offset.learn. There's just so much happening. It's difficult to make sense of all of this without sitting down with pen and paper.
Yeah, or maybe running through.
Yeah. Do you want to run through?
No, I mean like by running through, I mean like making change, like basically writing tests that you can run
Ah,
and observe, like make changes and observe like what is
yes,
doing.
yes, yes. Yes,
That,
that's
that
awesome.
that sounds like a good exercise for the audience. So
Definitely. Okay. And then in the end, they either encrypt or not, but in the end, they do something. Okay, they marshal it.
yeah,
Where did they add the bloom filter? BF.
I know.
BF.
So they build it here. I mean, whatever they want to finish like a block encryption or
Oh yeah, okay, okay. So they put it in here. They marshal it as JSON and put it in here.
yeah. So and I
Which
think
is
finish
which is
is
also in the protocol buffer definition. Estimated size, offset, and then the bloom filter. I imagine this would make looking up the values super easy without necessarily having to go deep into the offsets. I'm not sure.
yeah. I think probably we can. So based on this, the other part is their replay function.
Yeah.
So they have a replay function that is it's called at the beginning of, I think when doing Badger open, right? So the replay function,
Replay manifest file.
no, just the replay function in db.go. I think it's at the top, like.
Oh, okay. Oh, shit, this says test replay. I assume they'll be calling the replay function in here. Apparently not, it's recursive. Oh, no, it's not. So at the top of db.go.
Yeah. I mean, yeah, I think it's like the first function.
It's literally replay function. Wow. Okay. So what does it do?
Yeah, so it's called when you open, like you open the db.open, right?
Yes.
And it's I think it's used by the vlog to populate um
The tree. The skip list.
the, let me check, sir.
Because it looks as if, so the LSM tree is half in memory, especially the keys are pretty much usually in memory. So maybe that's what it's using this for, to build that, those keys in memory when the app starts up.
Yeah, that's what it does really. So it takes yeah, so the actual logic is, so this is like a callback function that the value log uses to build like the in-memory data. So it's, I don't know if we have the same. So I think on line 388, that's where it's being used by the value log.
388. 388 is an error. Oh, it's a
Well,
return statement, sorry.
oh, sorry, 386 for you.
Okay. db.vlog.open. Oh, yes, you're right.
So on opening, yeah, so it takes that log entry, replay log thing, which is basically the function that takes in each entry.
Yes.
So I think it opens the file, the file. Okay, yeah. So I think the file, the memory map file. I think it uses. So this is where the old memory map thing actually comes in. So
Flush and discard starts.
yeah. So here,
yeah, here I feel like it's just looping through.
and all the files, like I don't even know if there's a term for it, but the log files.
Replay log. There's a function called replay log.
And yeah, but it opens
function
the files that it wants to replay from, right? And passes to it.
Okay, replay log. Okay, there's so much happening here.
Yeah.
Justin, do you want to take over leading?
I
mean, you can share your screen.
Yeah, sure. I mean, I can.
Yeah, I think you also have deeper understanding of these areas than I do anyway.
I don't. Okay, so I guess probably I didn't go into that deep, but I mean, I could share what I went through. So I was like, since we've gone through most of the external parts, So one thing I don't really understand is this: they have like some sort of pointer mathematics. So I always used
Yeah,
to
I think I saw it. Like there's this value pointer stuff that they
yeah,
make set to
they keep
head.
resetting, yeah, the reset to head
Yeah.
or so I mean it's very hard. I should I say studying the code probably would not help with that really because um
Yeah, I agree. I was actually trying to go through the paper. Like, I think in the future I have to put in more, like, focus more on like studying the papers for this kind of databases before diving into the code. Even there are some theoretical things that I expect should be happening, but I have not yet been
okay,
able to
so I
find
didn't
it
know
in the
Badger
paper.
does Badger have a paper?
No, no,
Can
no,
you
but it's based, they don't have a paper,
oh
but
okay,
it's
okay.
based on a paper.
Oh
Whisk something something.
okay, so I think probably I never really looked into their I mean like outside the normal like documentation of how to interact with the library. I don't think I really looked into maybe more information about internal. So I mean, it's just fully code centric stuff that I've
Yeah.
been trying to figure out. Hmm. Okay, yeah. So of course, the paper. I mean, going through a paper was like some sort of thing related to what they are doing would
Hmm.
help. But of course, yeah. Okay, well, yeah, sure. So okay, since you even mentioned that it's, I mean, I guess it's the concepts they are using, right? Or it's not like Badger paper, like Badger.
No, 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 no. It's not directly about, but it's the same. Let me show you the paper. Whisk.
Oh, I like your background. Oh, what do you call that?
Okay. You mean this? No, not this. Yeah. This
This is what? Oh, yeah,
from,
yeah, this farm thing.
yeah. It's some tool I use for music when I'm working. It just plays music that helps you concentrate. Nothing more. And then shows cool pictures. So they have the paper. So anyway, this, yes.
Ah, really?
Yeah. And this is actually this concept of separating the keys from the values is what makes Badger faster than most databases. The idea that looking up, so usually in most traditional databases that try to do everything on the disk, they usually have to, when you want to do a read, they have to do all of the searching on the disk, which is, I mean, I don't know. I don't really know the trade-offs, but I imagine it's slower to do anything on the disk. Whereas Badger would, first of all, try to find the key in memory and then get the particular block where that value should be, and then goes to disk to get the value. Yeah, but just a dense paper, as you can see. So the best I did was to skim over it.
Oh, the reference levels DB.
I mean, yes, Levels DB, Rocks DB, those are the most popular players in the database space. So in the key value store space, yeah, Levels DB and Rocks DB. So everybody's pretty much trying to be better than them. I mean, yeah, so yeah, I just realized I can't even explain what's happening. Yeah, this happened. But
Okay,
yeah,
Oh yeah, okay. I guess that's where levels really got its name from.
Sequential random reads. I think one thing I noticed when I was looking at this paper is that this concept of a skip list, pretty much all of the databases follow that same concept. So what they do is that instead of writing each single request that comes into the file system directly, they keep some actually use a linked list, but most of them use a skip list. And what they do is that they write each single request that comes into the skip list. Then when it reaches this, like a particular size, which is usually the size of the block that they're looking for, they then convert, that skip list or the values in the skip list into a block, and which they store in memory. Actually, that is the concept. This LSM, log structured memory, I think.
Merge tree.
Log structured.
Okay, yeah, I think it's usually log structured merge tree. Yeah.
Yes. Yeah, log structured merge trees. So that's pretty much it. It's like a log of blocks, I think. So each of them is converted into a block and then stored. But I think the merge tree is that usually they merge multiple blocks together sometimes.
Yeah, it's like merge sort, right? Since the logs are sequential in time. So if you take multiple logs from different files, as in like let's assume they are logged in two different files, right? You can like scan through each one and merge them like sequentially because they are time logs.
So your voice skipped a bit. I didn't hear you.
Oh, okay. No, as I'm saying, because like since the stuffs are like time logged, right? You can iterate through each of the logs sequentially and merge them into a single one. So it's kind of like linear merging ish.
Yeah, I think like in this one, yeah, you're right. But I thought it was sorted by the keys.
Yeah, no, I don't mind me. I just said time. Like I meant something sorted.
Okay.
I mean, this is definitely, but the idea of saying logs is sorted by is log like sequential append only.
Yes. Actually, they said it here. The main advantage of LSM trees over other indexing structures is that they maintain sequential access patterns for writes.
Yeah.
Small updates on B trees may involve many random writes and are hence not efficient on either solid state devices or hard drives.
Hello?
Oh, someone joined?
I didn't know this thing was 10 a.m. I just woke up like what, like 10 minutes ago or something. I was thinking it was 11 and I was like, oh, let me come and join it.
Yeah, so Anthony has even fixed he has fixed the group permission thing. So we've created a calendar to easily, and there are already events on it, so it's easy to
Okay.
get reminded now.
Sorry. So what like we discussed? What are we looking at today? I'm not really sure. I know this is about the database, but I'm not really sure what's the
Yeah, so we and Anthony the person that is supposed to host us is not is it got occupied, I think. So I don't know if you saw the video from last week. We were looking at a Badger. It's also like a key value database, but instead of just in memory, it also uses persistent storage like your hard disk, right?
Okay.
So last week we started exploring the internals of how it works, and So it's a very large and complicated, at least more complicated than the previous ones we've been dealing with.
Yeah.
So we got to a point last week and said, okay, our last meetup and said, okay, let's stop here and
Yeah.
we'll
After
continue.
some
Yeah, I guess it was getting more technical and more technical. So
oh,
I guess so today, Anthony and myself, we kind of skimmed through most of at least the parts that were missing, right?
yeah.
And so I guess it's actually very complicated and very confusing. That I think studying the code alone might not help, as it might not help understand, except maybe there's someone that has an
Yeah.
expertise. So
Yeah.
Anthony brought up this that apparent it's based the design of the project is based on this
Yes.
whiskey or
Yeah.
wise key, I think. All right, so I think that based on our previous studies, it always makes sense to try and go through some of the abstract around it,
Yeah.
before going in. So was just trying to go through this, and yeah, I think that's pretty much the summary so far.
Okay.
I don't know if
Okay.
Anthony has.
Look. Okay, that makes sense.
Yeah, you said it all, really. But I've been noticing some interesting things. So just from reading this paper a bit, I kind of understood some of those things were like those value pointers that we were confused about.
Yeah.
So let me see. Boom, 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 boom. Anyway, so basically, what the whisk tree does is that it separates the keys. It separates the keys from the values. So in the LSM tree, it only keeps the key. It doesn't keep the values. You remember that in the beginning, we stored the value in a value log, like in the code, when we were looking at the code.
Yeah.
The first thing we did was to store the values in the value log, and then when we went down, sorry, always better to see it in code.
Is it here or DB? DB double. Okay.
It's here, I think.
Transaction.
Oh no, not here. Yeah, I think it's in DB. But let me go into the tests because I'll know my way around the tests. Updates, commits, commit and send. Send to right channel. Do right request. Funny how much I know my way around this code already. But yeah, so here, if you notice when we're writing a request, the first thing that we did is to write it to the value log. And in this value log, we pretty much just write the values. And now I'm reading the paper, it kind of makes sense. So we write the values. So you see here, they're writing each of them. But I think what is important, okay, what I assumed is that we build the value pointer from here, but I have not seen anything in the code pointers.
So yeah, can you see that P here?
That's P what?
Oh no, I was pointing to the P when you said the pointer.
Yeah, I just noticed. So yeah, so I think that's what happens here, even though I don't fully understand how it happens. But so the first thing when we get the values is that we write them to disk, and then we get a sort of pointer to where that value is stored. I'm sure if we check in here, we can see the file ID, the length, and the offset. So that whenever we want to look up the value, we just go straight into the file and go exactly to the particular offset. And we know the length, so we just pick the value out of the file without doing any much magic and jujitsu, which is super smart. So what they're doing is that in the tree, because the LSM tree is a data structure that needs to be sorted, Let me see the what's it here. Only keys are kept sorted in the LSM trees, while values are stored separately in a log. In other words, we decouple key sorting and garbage collection in whisk key, while level DB bundles them together. This simple technique can significantly reduce write amplification by avoiding the unnecessary movement of values while sorting.
Sorry, what is level DB in this context? Because is
Also,
I
I
thought
think
well,
this paper, no, this paper is just is I think it's proving its point against levels DB and rocks DB. I think they are the
okay.
what did Anthony call them? They are like the
Key value
guys.
stores. Yeah.
Yeah, they are like the
That,
popular.
how do I put it? So every existing database that we know, all of the popular databases, Postgres, MongoDB,
Yeah.
most of them tend to use one of these two, either levels DB or rocks DB behind the scenes.
Interesting.
Yeah, so they tend to use one of them. Levels DB was created by Google, I think, while Rocks DB was supposed to be an improvement on Levels DB created by Facebook, all with their different trade-offs.
What do you mean was supposed to be an improvement?
I mean, all of them have their problems. So people complain about Rocks DB because you need to do so much tweaking based on your hardware, based on the particular database types. You need to tweak so many things. So if you tweak it properly, it can be super efficient and super fast. But it's just like tweaking Java garbage collectors. If you don't know what you're doing, you're just going to make things worse. But anyway, so I kind of really like seeing what the paper just looking at the paper makes me understand the code more. For example, I've been seeing value pointer, I've been going through this code, but now I understand more deeply why it's here. So if we come in here, you can see that we keep all of the values. So yeah, the key is in here, but the most important thing is the value. So we just, it's an append-only file. We just keep appending new entries into the file. And I don't know what this SSC is for.
Sorry?
No, I didn't know what this SST file is for. But yeah, so we write in here, and then in the LSM tree, what we are dealing with would be the value pointers and not the actual values. So we can sort the tree, we can move around the tree, we can balance the tree without having to move too much memory around.
Okay, so I think so when I think so what that table builder builds is it the values, like it doesn't like write the keys or what? I mean,
no, I think the table builder is just for the keys. The values are in the value log.
okay, so like you remember we're looking at that finish function in table builder.
Yes.
Right? It takes the keys and values, right?
Yeah. So I think there is a kind of I don't remember where I saw that, but I think there's a kind of threshold. If the value is below a particular size, then they just keep the value as well. But if the value is larger than a particular size, then they skip it from the tree and from the block. So I think it's a kind of optimization. Get what I mean?
I think so.
Boom, boom, boom. So finish block. So here we add the Bloom fields.
Okay, so I think so. Probably we've not gotten to the end of our road then, right? Because if you look at the top, right, it seems they are adding, as in, so at what point do they encode the values that are to be stored? Because it seems all I'm seeing now are keys, as in, right? I mean, I don't know if you get what I mean.
No, for the values I showed you, the values happen much earlier in this vlog that's right. Encoding the values is a very simple process. They just
no, I mean like when is it
prepare
persisted to disk?
for the values.
Yeah.
It's here now. md.write. This is a file. md is a file. Write is a go function for writing to a file. See?
Oh.
So this operation here is actually writing to the file, right? To the actual file.
Okay. Yeah, okay. I think so. A lot of things are now coming to.
Yeah, exactly. Now it's kind of just making sense more and more. So for the values is super simple. There's really not so much happening. So they have a map, a list of files. So in this value log, they have a list of all the files that they are working with.
Yeah.
So they basically just get the latest file, the most recent file, which is max FID. So they get the most recent file, they get an ID for that file. They get the length, that's the existing length or the size of that file right now. Then they write the new values to the end of the file. And now having the original length, knowing the original length of the file, that is already the offset. And then they have the n, which is the size of what was written. So that's the length. And then they have the file ID, which is the three things that they use in building the value buffer, the value pointer. Remember, file ID, the length, and then the offset. Remember that the file IDs are numbers.
Yeah, okay.
Like here, integers. So they just name the files after the objects. It's actually, for the values, how it works is actually simpler than you imagine.
Yeah.
The problem is with the keys, which is this LSM. The process of encoding these keys, this LSM tree to disk, is what is confusing. So on a simple case, it's mostly just written into the tree, into the skip list, the memory table.
Yeah.
But encoding this memory table into this is where we have to do all that block building and all that stuff.
But I mean, like, yeah, but I mean, so it makes more sense now, right? Since like, so yeah, so I mean, they have this flush channel where they push flush tasks to when there's more, when the memory table is larger than the maximum size, right?
Yes, yes.
And the flush table listens to the flush channel, right? And the flush, if the memory table is why should the memory table be anyway? I don't know why. They are checking that it said if memory table is nil, continue. But anyways, so so when they get something from the but when they get a flush task, they call undo flush tasks, which so basically what flush task is doing is like flushing an encoded like key structure to
disk.
To disk.
Yeah. But it's doing it in such a way that it would be easy to do lookups.
Yeah. Like
so that's why in here it's having to do that. So I think it's in here, build table.
No, build L0 table.
Yeah. It's in finish. It's on that.
I know. Well, so build L0 table adds. No, I mean, right.
This build L0 table.
Oh no, it adds everything to the builder.
Yes.
It iterates through all the memory values, then takes their key and value, adds it, right? So this calls add helper, which now. Yeah.
Here's
Okay.
the best part. Okay, sorry. I thought I had a eureka moment, but I did not. Sorry.
So this is where it creates all the key hashes for the Bloom filter. Then
There's just so much stuff happening in this code base. Okay, maybe we should go back to that paper.
Yeah, it's but I mean, like, having all these characters, I mean, if I could, I mean, it's kind of almost easier to, let's say, you want to like contribute to this or build something similar, or
Yes.
have some logic that needs to undo, like undo keeping track of stuffs in disk while in memory, as in while holding something to find them in memory.
Yeah, like if you have some custom use case where you need to keep things in disk, maybe you still need some special way of sorting them, or, and you can't use a regular database. Oh, by the way, did you see that tweet I tagged you? Where Twitter solved their own problem using the same skip list which we studied last time. So, like, for example, Bloom filters, I've known about Bloom filters for a very, very long time, but I've always been confused about why would someone want to use a Bloom filter?
Oh yeah, I think I mentioned in the last video that okay, I don't know about many blockchains, but Ethereum, because Ethereum stores like events and data and stuff, right? So they tend to use Bloom filters to make it easy for you to know if in a particular block the event you are looking for exists in a transaction, as in like has happened in a transaction there, right? So all like blocks have a Bloom filter of events that have been triggered by maybe transactions or contracts or whatever.
Yeah, but that's true because you're working in that space. For me, who's not into the crypto space, I'm like, oh, this is a very nice data structure. I've learned about it. I know it, but why?
What?
So it's really nice when you're looking at practical use cases everywhere, and then even learning new data structures. I mean, we learned about skip lists, and then now we saw Twitter using it to solve searching problems in their own data centers. Now we've learned about LSM trees, so which you can pretty much use if you have that use case.
Yeah, I think LSMs are good for append-only writes and easy, like fast compaction of. Because I mean, if you have, so for example, I think they have it somewhere there. I need to look for it. But like, so all these, there are multiple like vlog files and pointers because they are structured in an LSM format, right? It's easier for them to easily just quickly compact some files together instead of having multiple.
But anyway, so just coming back, at this point, we built the entire tree into a table data file. And then the next thing we do is we reserve a file ID where we want to store it. Reserve file ID. Like this amount of atomic that is used in this code base.
Yeah, it's better than locking, you know.
yeah, I imagine. Next file ID.
Oh no, atomic operations.
Oh, okay.
They are guaranteed by the CPU to give you a value that has like without contention. So, but it's better than you locking your own process down and say.
Exactly. Actually, I think most mutex locks or all mutex locks are implemented on top of these atomic operations.
Okay. Yeah.
I remember checking.
Oh yeah, I think. Oh, sorry. I think semaphores are what I used to make mistakes with.
Semaphores are mutex. Oh no, sorry. Semaphores are not.
Because I think semaphores use more of atomic increments because semaphores, I mean, they basically guarantee some particular amount of access. Right?
Yes. I mean, semaphore is a concept. Yeah, you can implement semaphores with anything. You can even with a mutex, you can implement a semaphore.
But it's possible to do. I mean, like, I think they're like spin locks things.
So in Go, you can implement semaphores using channels. Like that, I implement semaphores sometimes with channels. just create a particular
Yeah,
a buffer,
I
a
mean,
channel of this size.
that's in Go now. Why are you starting yours in C?
No vex. No vex.
Yeah, but okay, so yeah, I think I don't know. Do you have any questions?
We also have the option of just keeping.
Baba, I don't have any questions. Oh. I don't have any questions. I've just been what's it called? Listening and trying to follow and trying to understand a few things here and there. But like in general, if I wanted to fully understand stuff, I'll probably have to do a lot of the. I'll probably have to check it out a lot more on my own. You get? So
Yeah. I think that's actually the idea of
yeah,
this stuff, is that we all look at it together, then we kind
yeah,
of share notes when we come
yeah,
together. Although we started earlier and we had this is part 2 of something we started 2 weeks
yeah,
ago.
yeah, yeah.
So that's why maybe you might be a little bit more lost, but it's just because we've done it before.
No, it's fine. So like I like there are some concepts that I'm still picking up, right? So like for me it's still a positive. You get?
Man, you should imagine all the concepts I picked up from just this code base. I'm still in shock. But yeah, but if you want us to talk about anything, you can always just mention.
Yeah, no,
All of
yeah.
us are learning.
If you have asked questions, if there were some things that I didn't get, sure you get. So I was asking, I've asked a couple questions. So yeah, definitely, if there's anything that I need you to that I want to understand better, I'll ask. Yeah.
Yes. So we're mostly just trying to understand how the database actually persists all the keys to this. So it's a key value store. It's a kind of database where you give it a key, you give it a value, and it stores that. Nothing more, nothing less. Key and value. But you would
Yeah.
not imagine how complicated storing a key and a value can be.
Yeah. So at least from what I've been seeing, it's like they store the keys in a data structure, but
Yes.
store the values in files. So actually, there's a question I wanted to ask: that aren't those files supposed to be like, I don't know, encrypted or something? Because it looked like you're able to browse the files and able to just easily identify.
Oh no,
Well, at least browse one of the files and be able to identify.
See, now, it roughly doesn't make sense. But so the keys are still string, the values are still string. You have the option of encrypting both the keys and the values, but you can also not encrypt them. By default, they are not encrypted. But it's a binary representation. That's why you see all of these binary characters that cannot be that you cannot view them.
Yeah, but if you can write something that can identify, if you know the format you store it in, you can write something that can identify the.
Oh,
But I
yeah.
guess since you say you can choose to encrypt it, then that makes sense.
Yeah. Even in the code, actually, I think we've passed some places where it's encrypted.
Okay.
Somewhere. Encrypt. Yeah, I don't know where, but I've seen it a few times. Yeah, encode entry, I think.
Yeah. Okay. Is it encode or be encrypt?
In the
No, I think I've seen in.
Yeah, if encryption enabled.
Oh, okay. Okay.
Yes.
Then there's also in the builder, in the table builder, so on the inside the finish method, I think there's an option to encrypt when encrypting those values. Right. Yeah, it also uses the same, like inside builder finish here.
Yeah.
Finish at the bottom.
Yeah, should encrypt.
Yeah, it should encrypt. Then if you
It
check
should
the
encrypt.
yeah, the encrypt function also does similar to what that one does. Like
Yeah.
generate and give you.
Makes sense. Makes sense. It makes sense that you have the option.
Sincerely, reading this code, I see so many things that I have to tell myself, Anthony, chill. You must not understand what's happening here. Focus. Every time I see all of this crypto stuff, I'm like, chill. Just move on.
Yeah. Yeah, there's so much. Like, I think, there's so much, honestly, like you might want to know about. But
They even have compression to compress data with different compression formats.
yeah, I think that's what leads to like what led to things like PhDs and all that stuff. Like, some people just felt like, you know what, let's just focus on one thing.
Exactly.
Uh,
But yeah.
So if you have a PhD in data storage or something very specific, you don't.
Oh, actually, I have a friend here in Germany, and I think he's doing a PhD also, and his PhD is actually on data storage. I remember having a conversation once, and all we're talking about was how much work like goes into all of these databases that have to write to disk, the ones that write to spinning disk. You know, this like spinning traditional hard drives.
Yeah.
How they're very different from the ones that write to SSDs. And I was just there acting like I understood what he was talking about. In my you know, like, yes. I did not understand Jack. But I mean, it's nice to see all of these things here too.
Yes. So I think at least for me, I told you when we started, for me, my question was really to understand how they were doing the whole like disk storage and memory handling thing. And I think I've covered like how they handle those two different things and how they are kind of making it efficient. Right?
Yeah. Actually, I'm not sure yet. So do you think it's okay? Let's just breeze through how the get requests happen. We've been looking at saving.
Oh yeah, I knew there was one part we never really went through. Yeah. But fetching should be straightforward now, right?
Yes, now that we know what's happening. Actually, I've gone through it before. It's straightforward until you need to go to disk. Because the way it works is that it tries to
goes through
search within. Yeah, it searches within those skip lists, those in-memory skip lists first. So I think it's this.
And by the way, anywhere you see things like MT is a skip list. So
a skip list is a data structure which is very similar to a linked list.
Oh, okay, interesting.
Yeah, the only difference. Let me just show you.
It makes it easier to jump to like further values instead of you going sequentially. So you can do some kind of binary search, kind of through
that is pretty much it.
Interesting.
Yeah, fuck. Yeah. So in a linked list, say one row like this would be a linked list, right?
Yeah.
And so if you want to go through, you have to go from head, you go to the next, one by one. But in a skip list, you start from the top. So let's say I want to find position 7.
Okay.
I'm going to jump to the next item. I'll check, is this thing less than or greater than 7? If it's not, I'll jump to the next one, and then I'll check, is this greater than 7 or is it less than 7? It's nil, so I'll come back. Or I would not just go there. Then from here, I'll jump to the next one and I'll check position 4. Is it less than or greater than 7? It's less than. So I'll jump to the next item. Is it less than or greater than 7? It's less than. So I now want to jump, and I'll now see that there's nothing there. Then I'll now come down one level. Then I'll now jump again and check. 9, is it greater than or less than 7? It's greater than. So I'll come back. And then I'll come back down one level and then go to 7, and now I'm at 7. So it's like, instead of walking one by one, you can just do jump, a series of jumps, and you're where you're going to.
It's useful when you have a lot of data, because if it's just small data like this, you end up shooting yourself in the foot. So it's good for like databases that are meant for storing a lot of stuff, I guess.
Mhm.
So I went to read up some more on the skip list a while back.
Yeah, I'm going to
What
check it
happened?
out because
Yeah, it's interesting. Twitter used it to solve some problems recently. And that was really exciting for me because I was like, yes, I know that shit.
I'll be now.
Yes. So let's go in here into get. So if you look at how the get process works, the first thing it does is that you give it a key. The first thing it does is that it tries to check within the current transaction if the value you're looking for was created within this current transaction you are in. So within a transaction, the transaction contains like a kind of list of operations.
Yeah.
Yeah, duplicate rights and pending rights. That's all the rights that have not yet been persisted into the tree and into the disk. So it's just check if it is within one of those pending rights. And if it is there, to just return the value. No need to continue searching further. Otherwise, it extracts the timestamp from the, or it appends the timestamp, the current timestamp to the key. And then that timestamp is very important because most of the blocks are kind of versioned. So you want to find the correct version of what you're looking for. So it calls this get function. And as you can see in here, this get memory table just gets the latest skip list. Or actually get all the skip lists. So it goes through the entire history of all skip lists. And then like it copies them. So because we don't want to create locks, because there are other processes, still writing to this skip list. And we don't want to lock the skip list when we are trying to find this value. So what we do is that we copy it and build a new list of skip lists. Cool, right? And then we return. So now we can go through those skip lists.
Manual reference counting.
Yes. They do some. So the manual reference counting is to help them decide whether to delete the tab. There's a file they create.
Yeah, I'm just.
But let's not go too deep into that. Yeah, it's really weird. Decrement. This will reduce the number. It's just a number. So anytime a value is accessed, we increase the number, and then when we are done accessing, we decrease the number until it gets to 0. So has perfect. Yeah, blah 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 blah. So all of this. So here it just gets that timestamp, which is at the end of the key, is this version. So we just get that version out, and then in here, as you can see, it loops through each of those tables, which is a skip list. Each table is a skip list. So it loops through each of them one after the other. I think it starts from 0. That's the latest, the most recent skip list. It loops through them, checking. So what it does is that it checks if it sees the value. If it gets the value, it now checks. I think it checks the version to see if the version. So what it does is that it has a maximum version. By default, that maximum version is 0. So when you get a new value, it's going to override this maximum version with that new version. And so to keep searching through all of these tables to see a version of the value, which is is more recent. So the timestamp is a higher number, which means that value is the latest version of the value across all of the skip lists we have. But now this part is super simple. The skip list is in memory, so all these operations are happening in memory. But if we do not find it in the skip list, which means maybe the value might be in the disk, then this is where the real shit happens. We go into the levels controller. And this levels controller is something I've read about like a million times and I still don't really understand. So bear with me. But I know there are multiple levels, level 0, level 1, and they are kind of searching within each level. But within each level, we run h.get in the level. And then, yeah, and this is an interesting part. So here we want to find a table that might have the key we are looking for. So if I remember correctly, what happens is that we compare within each table stores the largest numbers, the largest keys they have. And so we are comparing to find a table. Actually, it's here, sort.search. I'm going through all of the table. This is a Go.
Yeah.
Yeah, you can search any collection. So it's binary search actually. So we just keep comparing to see which table, any table such that the biggest key that table has is any table such that the key, like the biggest key it has is higher than the current key we are looking for.
Okay.
I don't know how to explain it. So like we might have table
equal to, yeah, as in, or is higher than or equal to. So that way we at least have the recent value, I think, and or a more or a newer value.
Yeah. So if you're looking for 6, for example, we're going to look at the first table, which the largest value it has is 5. So we see that there's no way 6 inside this 5. Then we look at the next one and we see that, okay, 10 is actually, 6 could actually be inside 10.
Yeah.
So in this case, we're going to pick this table to search within.
Okay.
So this is an optimization to prevent us from having to search for that key within all of the tables.
Yeah.
So here, what we do is now we found at that index, the table of that index that might have the value we're looking for. And we just get the table at that index, increase the reference, blah, blah, blah. But anyway, basically we return that table, which we suspect might have the value we're looking for. And then, obviously we iterate over the table. And
it's similar to the
actually, this is not really iterating. So why it's not really iterating is that we return a list of tables, but it's only one table that we actually return. I'm not sure why they did this, maybe to reuse some function. But in practice, really, there's no iterating happening here, because it's just one table. And so within that table, we now use the Bloom filter. I think we check, yes, it does not have. We check within the table. Each table has a Bloom filter. So we check if that table might contain the value we are using. You know what a Bloom filter is, right? Okay.
Yeah, I looked it up when you mentioned, Perfect mentioned, yeah. So I have a rough idea of what it is.
Okay. So it's just a data structure that tells you if it might have a value. It can tell you for sure that it does not have a value, but it cannot tell you for sure if it has a value. So that's why this function,
like really large data sets or something.
Yeah, it's super space efficient.
No.
You can index a lot of things, like billions of data sets within a Bloom filter of just a few kilobytes. And so, so here we know. So if it does not have, so we just continue. There's no need to search within the table. But if it might have, then we now just iterate over the table. it.seek. Seek from seek helper. So much, yes, something. So all of those blocks that we stored now we're now looping through each of the blocks. And then comparing the key. I think, if I remember correctly, we were also comparing. I really don't remember. I think we're trying to get. I don't remember what was happening here.
I think it's the comments now. So now we are dealing with the table of values,
Mhm.
the table of values that we like we persisted to this, right? So it's
No, this is
really,
the block. This one should actually already be in this.
and yeah, as I said, I was persisted to disk,
Ah, okay.
right?
How are we able to? So we are saying seek from key. Iterator.t. What is iterator.t? So let me just check. T is a table. What is a table?
Is the table you got the iterator from. Remember, inside when we were doing the gets, we created an iterator and then we created an iterator
Ah,
for the
okay,
table
yeah.
that contains the key, and then we use it to seek.
Yeah.
So
Yeah, you're right. So every block, this table represents a block and has a pointer to the file,
so
but
not a block,
also
it's a bunch of blocks, right?
okay.
So I
Memory
think
map.
that logic of the builder that we looked at, where when you call finish,
Oh,
it's like
you're right.
stop the block. So this is the table that it builds. So this is like loading everything back into memory, right? So it should have
Okay.
I mean all those, I don't know. Okay, the value pointer is used to. So yeah, okay, where does the value pointer now come into here? Because it seems they've already built the table up, right?
No,
Like
I think now this is for the key. These blocks only contain the keys or maybe the value. But remember, I think we need to find the key, like find a result before we would even now go to the value log to look up the value. So here we're just searching. Oh, dear. Seek helper. So seek block index. Block function returns a new block. Each block holds a reference and the byte slice stored in the block will be reused when the reference becomes 0. The caller should release the block by calling block.declare reference on it. Read, table.read. Okay, yeah, this is actually where it reads. So it either reads it, yeah, this is it. But before that, keep blocks in cache. So it tries to load the block into memory via the memory map. But sorry, let me backtrack. I think I'm a bit seek from. So we have the key.
yeah, so I
We
was looking at
search.
this search is a weird thing, right? Do you know why?
Yes.
I mean, number of blocks should be the maximum number of blocks that table represents, which is an
Yes. Maybe the
integer.
total number.
So now
Yes.
they are searching for an index that's why I don't understand. Like, what are they searching for? Right? I thought search should work, or maybe it's a different.
So the way search works, Go search is very weird. You don't actually give it the thing it should search through. It's just a binary tree, a binary search helper. So you give it the total size of what you want, and then you give it a comparator function.
Yeah.
So here now they're giving the total size of what they're going to be searching. And then in this comparator function, they're doing the comparison however they want. In this case, so if, for example, if this total size was 100, it means that with each, just like a binary search, with each iteration, it will be calling the function at a particular index. For example, if this was 100, the first call might call this operator with index
Okay.
50.
Okay, so that's what they now use to get like the block offsets within the table and get the
Yeah.
key. Okay,
Yes.
and then
So I guess yes. So
so
this
yeah,
based on this.
so they get the block offset at a particular index, and then
Yes.
so I'm assuming the key. Then they now check if the key is within that block. I'm sorry, if the
Yes, they're checking if the key of that block is greater than. They're comparing the two keys to see if the key of that block is greater than the key we are looking for. So kind of like binary search. So if it is greater, then we are going to divide by 2 and search the next half.
yeah, no, I get. I was just confused as to what they were trying to get there. Like, is that the index of the key or the block, or but apparently it's the index of the block. Oh, sorry, the
Yeah,
index
I think
of the
it's the
block,
index
I
of the
guess,
block. It's the index of the
that
block.
the value contains or the value is
Mm.
in.
Yeah.
Yes.
The
What is
block
this
that
KO?
like, yeah.
Because so it is protocol buffer encoded. So it's a list of
Yeah,
these PB encodings.
I think that's seems to be right. It contains the block information, the offset, the length, blah blah blah. Okay?
Since spending my brain. Okay. So if we go into this seek helper, after we've gotten the index, so I guess this is where we then search within that block. So we have the key and we have the block, the index of the block that might contain the key we are looking for. And then here we get the actual block. What is a block? So a block contains the offset, contains the data, it contains the checksum, entry index stats, entry offsets, checksum length is reusable. And then this is the reference counter for that garbage collection that they always do. Okay, so caching, block offsets. I guess here they just read in the block. They just read it from the memory map or from the file, whichever one is available, based on the offsets.
Yeah, and I guess it's because this memory map is efficient because I see a bunch of so many reads in the code.
Yes. It's efficient.
From files. Like
it's efficient because it just copies, it just maps it to a byte in memory already. So it's almost like doing an operation in memory.
And then you can easily seek to like where the, I mean, since you have a pointer to the memory, right, and you know the length of a particular block, right, so you can easily just seek to the end and get the next block. So that makes sense.
But I think it also, it's like a double-edged sword. You cannot keep everything in memory because you have a database that might be terabytes in size.
And also, I don't think it's memory. You know, I think the way memory map works is is it the CPU now? The CPU gives you a pointer to a particular place in memory, so you can start reading from there. So you're not necessarily like you are not necessarily, what's the word? You're not necessarily reading everything into memory.
Oh, actually, I think it does though. So if you check the Golang mmap definition, I don't know if I'll find what they call it.
Oh, yeah.
So how it works, Golang Unix mmap, because you just give it, take this one. I think we should do this one. Sys Unix mmap. So you see, you give it, I don't know what FD is. Okay, you give it the offset, the length, and whatever, and it just returns a byte. So I think the only thing that happens is that it keeps these bytes in sync with that file. So if you change the file, these bytes here that you have would also change. So it's still a pointer behind the scene. I guess Go just abstracts it. I can't jump. I thought I could do jump to definition.
GitHub is offline and GitHub.
Yeah, I give up. I break.
Yeah, I think it might be a system call or something. Let me check here. Okay.
Well, yeah, it's a syscall. At the end of the day, it's always a syscall.
Yeah, of course. Okay. I guess. But I mean, but at least it is better than like reading everything into memory. Right?
Sorry?
Oh, it broke. Sorry. I said, but it's at least it's better than reading everything into memory.
Of course, way better. And way better than doing it manually. Okay, so yes. So there's still so much happening and magic. But yeah, we get the block data. Whew. Wow. Let's just say at the end of the day, we return the block.
Yeah, there's a lot.
And then and then we do seek. Let's check in here. Found entry index, set index. Man, there's so much happening here. This is too much. I feel like this get operation is even just as deep as the writing.
Yeah, but I think the idea is, we understand the idea. The idea is there's a particular block format. I mean, they're basically just going through their file formats, like they search for where the block is, then they found the index of the block, and now we are using a block iterator to find where in the block the value is, right? So, and at the end, it will return the position of the value in the block in the.
Oh, wait, yes. So check this out. So all of that operation, like I told you, all of that operation we did is, I think it's mostly to get the key. But to get the value, we actually have to call this value copy, which seems to...
It copies it from the block iterator.
Come on. What's happened? On top of the qui a fallu.
Meta, this, that. Man, I give up. It's okay. We've learned enough.
Yeah, but I think it's just a necessary evil already.
Yeah. Gets.
It kind of makes sense. So,
It makes sense. But there's something I'm curious about. When we call, so let me just go back. When we call this.get, we get an item, but to get the value of that item, we usually need to call another function. I think we'll do something like itm value. So value is a function that accepts a function that accepts the bytes. So much callbacks happening. So let me just check on their website. I'm trying to understand.
Oh, you mean item?
Yeah, how they get the value
Oh,
out
there's
of
a
an
value
item.
function, right? There's a value
Yeah, but
function.
that function.
Oh, then there's value copy.
Oh yes, there's value copy. Maybe that's what I want. I want to see what value copy does.
Oh, okay. Let me see. I think it's somewhere inside iterator too.
Yeah, it's here. So value copy, yield item value, save copy. Yeah, it just copies.
By the way, Anthony, is it possible? Can you? Okay, yeah. Is it
Yeah.
possible for you to what's it called? Increase the size of the text a bit, like in your code, in your editor?
Like this.
Can you zoom in? Did you?
Yeah,
Okay.
yeah, that's better, I think. Yeah,
I should have been doing this all along.
yeah, yeah.
Every
It is
time
there.
when you're on a big monitor, it's easy to forget that.
Oh, yeah, that's true. Okay, that makes sense. Yeah, because it's bigger anyway. So
Yeah, makes sense. I'll be doing this in the future. Thanks for the feedback. But yes, so yield item value, we call dot has value. Besides, see, we got the value pointer somehow. See what I was telling you? Can you see? So when we actually get the item, we don't get the value. We might have the value if the value was small enough to be stored with the item. But it's until we call this value copy before we actually get the value. And it seems value copy called this yield item value,
Yeah.
which in turn it just decodes the value pointer from inside the item. Yeah, it just decodes that. And then it actually goes to the value log. Can you see? It goes to the value log to get the actual results. Not read.
Yeah, but oh, interesting.
Yeah, read value bytes. Get file
Oh, of
with
course,
log.
yes, man. I mean, it has to do that since all we've been doing since morning is actually only checking the key and offset bullshit on that.
Yes.
Pardon my, because yeah, the value is never actually there. That's actually
yeah.
All of that logic is just how to keep your keys.
yeah. Okay, actually, so then it makes sense to if the values are not there, right? It makes sense for for the memory map to still do some loading into memory because I don't think keys should have that much.
Yeah, they shouldn't be that heavy.
Okay.
And I think they are hashed, so keys should be constant size.
Yeah, but it's interesting actually. Because now I just came back to the realization that all we've been doing has nothing to do with the values.
Nothing at all.
So which means, so I'm just trying to imagine, let's say we want to build an improved version of this thing where you can do something like full text search on the values. It means you need to do some extra work to link.
Oh, you're right, man. That would be difficult. So there are two things you can do. You can store the keys with the value in the value log. So that when you do that full text search, you do the full text search only on the value log. And then you can now get the corresponding key and then look it up in the LSM tree.
Oh yeah, but I guess or maybe just make it. Yeah, probably. Yeah. Anyways, I guess probably at the point of indexing is when you index on the key and value pair while it's being added and not just on the values itself. Or else, yeah, of course, building indexes take a while. So you just build index, run through everything.
Full text search is a different kind of index. That's a big
Yeah,
matter that we know yet
that because it's because right now they are not technically in the same place, right? So if you get yeah, of course there will be something around it. He doesn't think about it. I just thought about that, like moving on.
Yes, I appreciate. So I think I've come to the end of all my realizations, and I'm happy with how much more questions I have. Yeah. But at least now we kind of have a clear picture of how the entire database works. There's a lot of crypto package magic happening here,
Yeah.
hashing and all that stuff. But I don't
I
think we need
just
to
be
understand
sure
that.
everything matters. So you're not returning
Mm.
the wrong value.
Yes. Okay, I think this was cool. Do you want to add anything?
No. Okay, do you want to add anything?
No.
Yeah,
Sorry,
it was
people.
cool. I'm
Yeah.
trying to imagine, do you think if like all these old okay, yeah, it wouldn't make sense really. I think all these compromises because you want to actually have them stored on the file, like on the file system or on a file system. Because if your constraints weren't that, I don't think you need to jump through all these hurdles. I mean,
Yeah, I
like
think the
we saw
approach BondsDB.
with BondDB, yeah, you don't need to jump through all this.
Actually, sincerely, I feel like if I want to use a database now, I feel like the BondsDB approach is really better for most. Very few domains would have to deal with terabytes of data. Very, very few. Most applications you build, all of your data would be able to fit into, I don't know, even for a big company scale, would be able to fit into a few gigabytes. So just keeping everything in memory would already give you a very, very fast system.
Because now I'm thinking about this. Anyway, a memory map over like so if you have like some sort of network file system and all that, that will also because if you are dealing in large like you probably okay maybe you set up some sort of log rotation. Honestly I don't know. Because I'm saying if you are dealing in large systems, right, it means you probably have a network file system that your Badger is interacting with, right? So that kind of I don't know, does this work well in that kind of scenario? Because right now we're assuming all the old file systems are kind of native to where the application is running.
Yeah, actually.
Because we are running like a terabyte system that builds a terabyte of data. Does it make sense to just store everything? I mean, we just keep compounding this or just have some sort of network file system with some mapping architecture to ensure
actually all of these databases, all of them, they expressly state what they are optimized for. So this one in particular, Badger is optimized for SSD. So if you are in a Kubernetes system where your storage is over network, I think this is going to do very badly.
Terrible. Okay. I guess it's good that we noted that now.
Yeah. I think this is not what you need in that scenario. Actually, I think if you're running in that kind of system, a BondsDB kind of system would still work very nicely for you.
Okay, you
just loads.
But then you use something like their like Rust or something like that.
Oh no, I'm just assuming. I mean, I'm assuming you want it to be single tenant. Yeah.
Yeah, it doesn't help.
I mean, this one also does not have Rust. It does not have replication. So.
Yeah, it doesn't.
But
anyway, it's good. I mean, at least they all have their use cases, which is very good.
Yeah, sincerely, I think for most systems, if I'm starting a project, and now I feel like I'm going to lean more towards just putting things in memory. All of this complexity, it's super fast. Badger is super fast, but you can never disagree that there's no cost behind all of this logic. See how much logic is happening everywhere.
Okay, I guess so. Maybe if we actually look at it from a practical angle, right? The truth is, it is, what's the word? There's more resource on your SSD. Like, I'm not mentioning like
Mm-hmm.
going terabytes now, right? There's more resource, as let's assume you have like, so let's say you are building a desktop application, you're using Go.
Mm-hmm.
This desktop application probably keeps track of, let's say, maybe some game assets, right? Like,
Yes.
I don't know how much that makes sense. But basically, what I'm saying is this: like, there's a limited, like, is more limited. You usually have more limited, like RAM memory space than your file storage space. So if you are running, um, so for example, I'm in crypto, right? Most of the crypto projects tend to use this guy Badger, and it's because, like, for example, you're running something like P2P, like all these IPFS, peer-to-peer stuff, right? And you tend to keep
Yes.
track of so many peers that are connecting to your guy, and then you're also trying to do some file metadata storage and all that, right? I guess it is
Yes.
easier for me to have like 32 gigs it's easier for me to have like 16 gigs of file storage than having
Yeah.
16 gigs of memory.
You're
I don't
right.
really get
You're
what I'm
right.
saying, because there are some other things that will be running, a bunch of Go routines and all that other stuff. So I guess
You're
for that
right.
scenario, it kind of works. But if you're just doing small caching, like maybe you're doing a simple app where you are trying to cache the navigation state or something. I mean, like,
Yes.
what do you need that for?
No, you're right. You're right. But me, I'm turning more in like for normal web applications, for example.
Yeah, that's what I'm
I
saying.
need to
Like,
store
web application,
states.
you're just storing, like, yeah, you're storing navigation states.
No, not navigation. Even user information, like you're storing profiles and accounts and all that shit. I
And
think I'll
yeah, no,
still
I wanted to make it
put
sound
it.
ridiculous. That's why I said navigation.
Because this data is usually not so heavy. You can have thousands of customers and all of their data would still fit into a few hundred megabytes. In my company, we have like, I don't know. Let me not talk about my company so that this is going online.
No,
But
no, but you
yeah.
can. No, okay. Oh, okay. That's fine. I mean, you can give the same kind of details that are already public, I guess. Like, if
Not
you want
some
to
that
talk
I'm doing
about,
in my team that is not public. But yeah, you can have like thousands
We
of.
don't know what was in his contract. Probably his contract says don't say anything about the company.
Exactly. Yeah, I didn't even know that contract.
maybe on the website, because I know it's very common for people, like for organizations to say, okay, we serve what 25,000 clients or something like that. Sure, you get. So
No.
that's what I say. Like if they already say something like that publicly, then
But I don't.
like,
It's easier to stay on
but according
SSC.
to Perfect, maybe the design should not say anything, whether we've said it or not. Maybe if they say it should just be fine. So yeah, that's fine. Please, let's not get you fired.
So yeah, but yeah, you can have like thousands and thousands of vendors, for example. Okay, not vendors, but someone else. And it will still fit within like a few gigabytes.
Yeah.
So it's cheap to just get a 4 gigabytes RAM server, and then you have a blazingly fast application forever.
Yeah.
Yeah, well, true. I know most companies that do real time, like, stuff, they tend to use the memory strictly, like,
Hmm.
still large
Yes,
RAM.
yes, which makes sense. But also, a lot of these companies that are working at scale, sometimes the scalability problems they have is due to inefficiencies along the way, like inefficiencies from the database and all those layers. For example, if you have a
Yeah.
database that is taking 500 milliseconds to process a request or to give you back a response, and then within your server, pretty much your server now is waiting 500 milliseconds plus maybe its own 200 milliseconds to do an operation. This already automatically and by default limits how many requests the server
Yeah.
can handle at a time.
Yeah.
Yeah.
But if you have a server that is handling requests within 15 milliseconds, it can handle way more, like maybe even 100 or 1,000 times more requests per second. And so you end up needing less resources just because you're using an in-memory database that just keeps everything around.
And I guess most companies do. I think it's a trend. Most companies don't do like most of this profiling thing until at the
Becomes
beginning.
a problem.
Until you start going large, right? I was reading. I think everyone you've all probably read this Discord story. Like when they moved from Go to Rust and stuff, right? But
yes.
that one is a different thing. But like from what they said, although I don't know if it's true, but they are basically saying they keep track of everyone online, like your online status per.
Yes.
I think they keep everything in memory on a single.
Yeah, I think I saw it. Yeah, I saw it.
And I'm like, wow, like how many gigs of RAM are they loading them? Because I assume they have like hundreds of thousands of users. It's a game. It was initially a
like
game.
I was telling you, it is also. See, even 1 billion users will still not use as much memory as you think, because those kind of information are very, very small.
Yeah.
Like it will be in bytes.
Yeah, it's not like their full history. Okay. Yeah.
Yeah. So even if it's 1 kilobyte, which of course we know it to be in bytes, but even if it's 1 kilobyte and you have like 1 billion users, which I don't think there are 1 billion users, we dash them. But let's say they have 1 billion users. This will still be 1,000 kilobytes, which is 1,000 megabytes or 1 million megabytes. Oh, you're right. This is 1,000 gigabytes, which is 1 terabyte. But you're assuming that each of the users' information.
So,
yes,
and
which
again,
is still doable. This is still doable.
Yeah, 1 KB is still relatively large for
large.
data.
Oh yeah, keeping some meta information about a particular person.
Yeah.
Yeah, but I guess I think I find this conversation interesting really because sometimes all these problems and stuff you probably
it's an experiment
system until you start going large and then you realize that probably it's just best to keep everything in memory.
Yeah, absolutely. Absolutely.
Yeah, just
use
memory.
It makes sense putting time into optimizing something that you don't even know whether the business will succeed yet. You don't even know. You don't even know whether you get.
But we are engineers. We're engineers.
Yeah.
We will not hide that part of us.
If you know how to avoid some of those problems in the first place, then sure, if it doesn't take time. But
this is something I want to explore more and more. So like systems I build in the future, I want to rely more heavily on keeping things in memory, like systems, even like just in memory. I want to try to do more in-memory key value stores, or even if not key value, but just in-memory databases without the network. So I can't really use something like Redis. And I imagine that the systems will be really, really fast. Maybe single milliseconds.
Okay, but are you going? Yeah, sure. Is your requirement also to ensure like persistence or?
Yes, with persistence. BadgerDB does persistence,
I'm saying like consistency, really, right?
Bro, let me tell you, there's none of the systems we build are as consistent as you think. Mention any database.
I'm asking, like, because when people do large scale like in-memory stuff, most of the things they put in there are things that honestly, if they get lost, it doesn't really affect like.
Yeah, but when you see something like BadgerDB that is persisting every second and still has it persists every second and it still has hooks. Such that, you can put in hooks such that if your server is shutting down, it will still persist everything before it shuts down. So at the end of the day, you really, except like there's some crash, like hardware crash or something crazy that, I don't know, did not give your server enough time to, did not give the operating system enough time to send out
Signals,
shutdown
yeah.
signals, then I don't think you can really be afraid of anything. And very few systems are that consistent. We're not building financial systems where 1 second of data.
Well, I work in the financial space, technically.
Okay,
So.
I'm sorry. This does not apply to you. Please ignore everything I said before they fire you because of me.
So, but anyway, yeah, I mean, this was fun. I think, I don't know if there's any questions, contributions. I think we're just over the 2, or almost at the 2-hour mark. I know we started a bit later than normal.
That's okay.
So,
This was
I
fun.
don't know, any questions, additions, subtractions, duplication?
Nothing from me.
I really wish Kenny, is it Kenny or Kendi?
Yeah, Kenny. Both of them.
Kenny was here because I'm sure you must have done a lot more like deep work on this. But,
Yes.
but anyways, it was nice. So I think for next time, probably looking into networking, into like a networking project.
Do you have something in mind? Or do you have something in mind? So you've not presented
So,
yet.
I mean,
Maybe you can try something.
Okay, yeah, two actually.